Oh, what a long day! So much work. YouTube. Yeah, this is good. This is so good. Oh. Gotta find Bettine and Renee. Hey guys, I found the perfect topic for us to do. How to rotate a perfect sphere using a water jet.
To understand the phenomenon of a ball spinning on a jet of water, let's introduce two fundamentals of fluid mechanics, the Bernoulli equation and Bernoulli principle. The formula for the Bernoulli equation includes the pressure head, which is the energy developed in a fluid in a closed conduit due to the presence of greater than atmospheric pressure, and is expressed in meters. The Bernoulli principle shows that a high velocity gives a lower pressure and vice versa. In addition, objects have a tendency to move from high to low pressure. The following demonstration is used to describe how a vertical jet of water can rotate a spherical object.
Coming on to the free body diagram of what's happening. The pressure or the force of the water comes up and hits the ball right at the sweet spot, right in the middle. Now we have another force going down, and that is the weight of the ball. So we can express that in terms of Fg, the weight of the ball, is equal to Fp, the pressure exerted from the water coming up. Rearranging this term, it's pressure equals the weight of the ball divided by the area. Why does the ball rotate? Let's look at this diagram right here. So what we have is a velocity profile. Now this is the water shooting up. As you can see at the center line, the water moves faster than at the edges. So what we have is the water in the middle hitting the spherical ball faster than it hits the edges. Now, here it creates a low pressure area, while around the edges, it's a high pressure area.
Now let's do an example using the Bernoulli equation. We're given the parameters V1, V2, and the second pressure head. Notice that V1 is less than V2. We assume no losses and that Z1 and Z2 equals 0. Using the Bernoulli equation, we substitute the values and find that the first pressure head is 8.8. This shows that with a lower velocity, you achieve a higher pressure, and with a higher velocity, you get a lower pressure.
Using another example, an airplane rises due to the differences in pressure. When air hits the wing, air particles above the wing travel faster than air below. This means the pressure is low at the top and high at the bottom, which causes lift. Thus, we can conclude that objects move from high pressure to low pressure.
Back to the spherical ball. We know that objects move from high to low pressure. So when the force of the water comes up and hits it at a low pressure, the ball might want to veer off to one side. However, the high pressure brings it back towards the low pressure, which causes it to rotate.
In this example, we have a pool ball sitting on a pipe. You can see that the cross-sectional area of the pipe is too small for the weight of the ball, and the ball does not spin. Now the pipe has a larger cross-sectional area, and the ball is successfully held up and spins.
Here we have the same size pipes with two balls of the same diameter. However, the ping pong ball is much lighter than the black ball. You can see that the ping pong ball cannot handle the same amount of pressure that the black ball can. This shows that the force of pressure required is proportional to the weight of the ball.
Now, this much heavier ball is able to spin on the same diameter of pipe, but requires a higher pressure to account for the increased weight.
This final example shows that the object must be spherical in order to rotate.
What if we use air instead of water? Here the air moves around the sides of the ball at a high velocity, creating a lower pressure than the surrounding atmosphere. This scenario differs from water because with water, the pressure difference is formed within the jet itself. This localizes the pressure difference and allows heavy objects, such as a bowling ball, to be more easily spun than when using air.